Just a brief introduction. As Kieran said, Jose has been here for several times, and before also the IIS, Jose came here on a Leverhulme visiting professorship also, and other visits too. The Royal Society, I'd like to say that it's the first Royal Society Wolfson visiting fellow here in Latvia. This is the information I got from Laura. So very brief introduction. Jose got a PhD from IMPA in Rio in 1997. Rio is a very prestigious mathematics institute. For example, one of its products is Arthur Avila, who is a Fields medalist. In mathematics, Fields medalist is the equivalent, maybe more difficult than a Nobel Prize winner. All right. The contributions of Jose to dynamical systems are crucial. For example, the work of Jose with Bonetti and Diana in 2000 is a cornerstone publication in partially hyperbolic systems published in Invenciones. Today, Jose is going to talk about fractals. It will be a general talk, my understanding, not very mathematical, targeted at general.
Yes, thank you. Well, first of all, thank you for the invitation. It's always a great pleasure to be here, specifically IIS and more generally at Loughborough University. Well, this is my second sabbatical here, so I don't need to prove that I really enjoy to be here. So as Wael said, the first one with the Leverhulme Trust grant, and now with the Royal Society. So I'll be talking about fractals, and I'll try to make it accessible to non-specialists, non-mathematicians, and interesting for mathematicians, which is very challenging to. The most difficult talks are the talks like these. Talking to specialists is very easy. Well, talk about your last results, and it's the best you can do, and everybody understands, especially if you are among specialists. Here, it's not directly related to my work, but in some sense, I could make a bridge, but I decided not to be technical. But it has to do with a preprint that I've posted of a joint work with Wael, which has some fractal component. Hidden is not the main point, but in some sense, it's related to that. So it's not that far from my current work. So I'll talk about fractals, of course, from a mathematics perspective, but I'll try to enhance some ideas of fractals that we can find in some arts like painting, music, and literature. These are the three. I'll make some reference to it. Well, I'll start with a sentence from Galileo Galilei. Maybe it's written in Portuguese. Galileo, I think in English is with O at it. Yeah, okay. So it was translated. I forgot that the names need to be translated as well. So now you learn Portuguese. This is Galileo with U. And actually, I don't know in Italian. Maybe it's with O.
Yes.
Yeah. Well, Portuguese decide to innovate. Okay, so Galileo said written somewhere that the universe is the language that describes the universe is mathematics, and its characters are triangles, circles, and this is the part that I'm most interested here is other geometric figures, because well. It goes to the classical Euclidean geometry, triangle, circle, and so on, but knows that to describe the universe, other geometric figures are needed. And this is actually the goal of this talk, is to make you see how fractal geometry can be interesting to describe the universe, well, some parts of the universe, some components, and as I said, in particular, the art. I would like to add to this sentence maybe my favorite definition of mathematics due to Poincaré, Henri Poincaré, one of the greatest mathematicians of the history of mathematics, which says that mathematics is the art of giving the same name to different things. The goal of the mathematician is to identify patterns, to establish language, and then look at things in a very specific way and identify those patterns. And from that, using the background of mathematics, can deduce a lot of things. So that's why I like very much this sentence by Poincaré, which is related to the previous one. So it's not just the language, but also the patterns that we identify. And here, the patterns is the fractal geometry. So I'm going to show you some images just for you to start. I imagine you all have an idea of what's a fractal. I would like, at the end of the talk, at least you to understand, for those who don't know yet, I guess many of you know what is that image that appeared in the first slide under my name. At least for those who don't know, to understand a bit of that. I'll start by introducing some images. So this is a heart. I think this is a bit of the coast of the Ireland, southwest. At least I went to Google Maps and it looked like, I thought it was Great Britain, but it's in Ireland. These are clouds, a fern, landscape mountains, and here a tree. Well, we look at this and we see that we cannot describe this with the classical triangles, circles, so we need some richer geometry to describe this. So these natural things that appear, here some human production, which also is around that idea of fractal that I'll try to introduce later. This is due to Escher. This is from some church, I don't have the reference, but well, this is Pollock, a painting of Pollock. So this, the three above, non-mathematicians, so nothing directly related to mathematics, even though Escher has some mathematical thinking. And the three below, well, this is the one I mentioned before, so the one that appears in the first slide. And, well, you may look at this and say, why isn't this one in the previous one? This is a fern. And I'll show you that this is actually a production, a human production actually using fractals. Okay, so I would start with this fractal, saying what is non-fractal first of all, fractal, there's not a definition very precise, so it's an idea. So it's an approach to some type of structures that we see. And there are some components which we'll identify here. So, but first I would say what is non-fractal. So non-fractal is something that we magnify and we still see the same. So look at this arc here. We magnify it and we still see an arc, and we magnify and we still see an arc. So there's no new structures appearing. Fractal, well, you have seen here this curve, and it seems that it's somewhat smooth here. But when you magnify, well, you have to have some goodwill to. When you magnify, you see something like looks like. So this is the magnification of the. Of course, this is very. It's not thin enough, but when you magnify this, you see something which resembles the previous image. And here it seems like it's very regular, but when you magnify, you see something like the initial or the previous image. So magnifying a fractal object reveals new structures and something that on a certain scale looks like some smooth line. When you zoom and you see something which is not exactly what it's in. So the scale is important. So for non-fractals, I would say that there is a single natural scale. For fractals, there are several scales. Okay, so the term fractal was introduced by Mandelbrot in 1975, and it has actually this figure is the same that appears in the beginning. It's known as Mandelbrot set. And I would say that there are three main ingredients in fractals. One is self-similarity. So you magnify, and at a certain moment, you see what you have seen in larger scales. So scale is important. Depending on the scale you are using, you can see one thing or you can see something different. And dimension is a very important ingredient. Is perhaps the more interesting from a mathematical, at least in the field I work, is perhaps the most interesting ingredient. We all have an idea of dimension. A line is dimension 1. You use one coordinate to say which point you are. A plane is dimension 2. Space, 3-dimensional, where we live. If you add time, you can have 4. Fractals are characterized by fractional dimension. You may wonder what is dimension 1.5. So for dimension 2, you have 2 coordinates. So what's half coordinate? Well, here is where mathematics appears and captures dimension from the dimensions we know in a different way, not using the number of coordinates, using something different. Okay, let's look first at self-similarity. So there's this famous picture by Sierpiński known as Sierpiński triangle. Well, you go to a triangle, you divide in this way. And so you have here 3 triangles, like the first one, just reduced in scale, and then you divide again, and you create this picture. And here you have a dynamical, so you are seeing certain moments, you see exactly the picture you had in the beginning. Well, we can identify this as a cathedral in Italy where the same idea appears. And so this is from the 12th century, so a long time ago, this idea appeared there. This is somewhat related to something which is known as the chaos game. Fractals and chaos are very much related. Well, the idea of the chaos game is we put 3 points, can be the vertices of the previous triangle, and you choose randomly a point, and then you choose randomly one of the 3 vertices. And you walk halfway to that. Here, the first choice was the choice or random choice is vertex C, and then you walk halfway and you point back. And then the second choice was A, and half and you point. You draw this point. So the third one was B, and the fourth one was B again. So you were here, then you go here halfway, and then you go halfway, and you iterate and you mark these points. Well, why game? So this is just a procedure. Why game? Actually, there was a very nice. This is I think in the web page of Devaney from Warwick, right?
No, he's in Oxford.
Okay. Sorry. It's no longer available. But I decided to put it. It was nice for kids, for instance. You had. I think it's because of the applets. You decided not to update it, but it was nice to play this. So the idea was given an initial point, and by randomly choosing one of these triangles. Of course, novice or master, more divisions, smaller triangles, the number of iterations you need to arrive to that triangle. This is the game, okay? Okay, so, but what does it have to do with the Sierpiński triangle? Well, here you see the number of iterations. You have a random process. You are marking the points where you fall, and what do you get? You get, in the end, in the limit, you get the Sierpiński triangle. Okay. There are some variants of this procedure. So instead of triangles, we can have something spatial in dimension 3. So these are random processes generate well-defined fractal objects. Okay. So a bit of mathematics related to this. To describe what I said before, now from a mathematical point of view, and then to generalize to other situations. That's the nice part of when mathematics intervention of mathematics to then generalize and produce more things. So here we put a coordinate system with 3 points, and then we have first random point, and then what we do. So n is 1, 2, 3 are the 3 p's, and then you take the previous one. So you start with z0 or z0, and then you produce z1 by randomly choosing one of the 3 points, and then you take half of the middle point between the previous one and that randomly chosen point. So these 3 triangles, the ones that we remove, so we divide it this way, we remove this point. This is the first stage of the process to produce that Sierpiński triangle. So we can describe these 3 triangles as a transformation, and here is the transformation. It's very simple from a mathematical point of view. For those who don't know much mathematics, it can be very weird, but it's simple. So we have 3 transformations because n is, so W1 is this one here, it's related to P1, W2 is this one here, and so this is the image, actually this is the image of the full triangle by one of these 3 transformations. So the only thing that changes is the reference point, P1, P2, or P3. Okay, so this is the algorithm. So from a mathematical point of view, it's very simple to describe. And so the Gauss game can be now described in a mathematical way. So it is the same. So you use the transformation. What we choose now, instead of choosing the point, you are choosing the transformation. Okay, so this is the mathematical way of describing that problem. So let's consider now, using this idea, a different situation. So imagine now, instead of a triangle, we have a rectangle or a square. Here actually is a square, 10 times 10, I think is the length. And we have, instead of 3 transformations, we have 4, which geometrically act like this. So this is bigger. So all are contractions. But this does not contract that much as the 4th one. Here, the way we describe these transformations, and we use the same algorithm. So we choose randomly an initial point, and then we choose randomly but biased in a certain sense. So the probability of choosing this one is much bigger than the other ones. Okay? So it's the same idea. Okay? So this is actually part of a mathematical theory, a part of dynamical systems, which is iterated function systems. What does it produce? This is the interesting part. Oops. Maybe I should have tried it before.
Oh, is it one of the video files in the
Yeah.
switch over if you like?
Yeah. I thought it was the first.
This one?
Yeah. Produces here, this one. That's why I said in the beginning that in those 2 slides, the fern apparently should be in the previous one, but it. Okay. Okay. So you see a way of producing that image, the fern, from a mathematical point of view, can be in this way. Using the classical methods of geometry would be difficult. In this way, it's very simple, especially with computers nowadays. It's very simple to produce that. Okay, so actually this fractal, here we have another, it's a fractal landscape. These ideas, these fractal geometry techniques have been used, in fact, at least for these 2 films, the Star Wars and Star Trek. These ideas of fractal geometry have been used to produce landscapes. With ideas around the algorithm I've described before, of course, with some more complexity. Oh, here the movie works. Great. So we put a grid, and then we randomly choose. Of course, there are transformations associated, and you iterate the process. That's what it's doing here. So it's from this side. Okay, and then of course comes the artist paint, make it seem real mountain in this case, or an island, something like that. Okay, so this is around those ideas. So this was self-similarity. We are iterating processes where we see in small scales what we have. So now comes scale. Scale is very important. For instance, to measure the British coast depends on the scale you use. If you use a scale of 500 kilometers, the size you put here 500 kilometers there, the size will be the perimeter will be 2.6 thousand kilometers. I'm sorry, everything is in kilometers, not in imperial miles. I decide not to translate too much. Okay. But if you use a smaller scale, the size is the coast is very wide. And see, if you go to a very small, it is much bigger. Okay, so scale is important. Especially if, of course, if it were straight line, scale was completely unimportant. Okay, it's because the coast of Britain in particular is very irregular, fractal in some sense. We'll come back to it. Related to this is another important object in fractal geometry is Koch curve. Well, we start with an initial length, well, 1 decimeter is usually an important one. And then we divide in the middle in 3 parts, equal 3 parts, and we put the same size and we do like this. Okay, so this is the first iteration. Next iteration, we come here, divide in 3 parts and do like this, divide in 3 parts and do like this, divide around. Okay? So, but length. So it was 1, 4/3. It's very easy to see it's 4/3. 2 iterations. We have, well, it's not difficult to see that we have this formula. It's, well, in 2 iterations is less than 2 decimeters, but didn't increase that much. But, well, it seems that we are iterating process. We can iterate easily, for instance, 100 times. And in 100 times, we have more or less the distance, it's a bit less, but the distance to the Earth, to the Moon, is less than 400,000 kilometers, meters, or 400,000 kilometers. Okay. So it's of the same order of the distance to the Moon. It seems that iterating 100 is just a matter of being here, being patient several days. We produce the distance from Earth to the Moon. Actually, the length of this curve is infinite. If you iterate it infinitely many times, it produces a curve with infinite length. Well, what is infinite length? You can think, well, it means that if I give you any sufficiently large number, there is a sufficiently large number of iterations for which the length is bigger than that. Here's a variation. It's interesting. So you start with a triangle, you produce triangles. This is known as a snowflake. Okay, so scale is important. Well, some variations. Here you do, instead of doing like that, you do like this. The final will be something like that. This is very interesting. Actually, you can go more than 1 century back in mathematics. You can go to Hilbert, for instance. And so this idea of having curves that fill a square, for instance. And it was proved that it is possible to continuously, it's not just curve, it's a continuous curve that the image of that curve fills in completely a square. And we can describe it in a very simple way using these ideas. Well, here we go again 1/3, you go up, then you go down like this, you come back. So it's a bit more complicated, but in the end, we produce a curve which fills in the square. And also we can use those ideas to produce things like this. These have been produced by algorithms around this idea. About the space filling curves, well, sometimes when I was introduced to this Hilbert curve, the professor at university talked about that as something pathological in mathematics. And well, from a mathematical point of view, very interesting in terms of applications. Well, nowadays we always listen to what's the usefulness of these. Many years after, actually, Luis Velho and Jonas Miranda Gomes are from IMPA in Rio, from computer graphics. And they used this idea of space filling curves to produce the digital halftone, which is very important for printing, for printers. The idea is what you see, so starting from white and going to black gradually. And you can see that the traditional method was that, using the ideas appeared in a paper in computer graphics, which we look at that and say, well, this is actually much better than the previous method. So using these ideas of space filling curves. So usefulness as well here. So, and the third one, dimension. Well, here I have a segment. This from a technical, the dimension there are many ways of introducing dimension, many dimensions. From a technical point of view, this is the box dimension. This is the simplest. For no specialist, it's the best one. For specialists, maybe not the best one. So we all have idea that, so the object here is the blue, the segment here. It's a one-dimensional object. Well, we strip it's not one dimension, it's two dimensions, but I think it's just a segment. So the idea is think of squares squares covering this segment. How many do we need? Well, it depends on the sides of the square. Well, if the side has exactly the same length of the segment, one is enough. So that's for when the length. Imagine the length is one, and so the length of the side of the square is one. So if you use the same unit, the number is one. But if you go to 1/2, then you need 2. Okay? And 2, well, it's very deep from the point of view, so it's 1 over 1/2. And then if you go to 1/4, you need 4. If you go to 1/8, you need 8. So you see that if you use a certain length, you need 1 over L. This is the number of squares of that length, the side, to cover the initial object. Okay? Let's go to the square. Well, if you go, so this is the square, the same length, 1 is enough. So here is the same. But if you use of half not the length now, but the length of the side of the square, now you need 4. Not 2 as before, so we need 4. And we go and we produce those. And you see, it's not difficult to see, that we need 1 over L to the power 2, 1 over L squared. Wow. Well, there's something here that maybe we don't need a very mathematical spirit to see. Well, here dimension 1 appears, well, it doesn't appear, but it is here 1 is invisible, but there's a 1 is 2. And that's the way we define this box dimension. So the number, so you give, these are very regular, of course, to present you the definition, I present you definition with something you know very well. So for this something, which is a segment of square, it matches the definition. And for the known objects we know the dimension from other perspectives, number of coordinates, it fits that definition. So this is the way we use many times in mathematics. We go to something we know very well, and we try to see the aspect here is dimension from a different point of view in such a way that we can generalize. So let's go now to other not so simple objects and try to see that what is the dimension of those objects, and we will realize that fractional will appear. So this is just this a bit of math. So so n is 1 over L to the d, so d will be the dimension, 1 or 2 in the two examples. Here we can use math. So the mathematics to realize that d is use logarithms and we isolate d. And if for self-similar objects, if we have a certain scaling factor, like in the Sierpiński triangle was 1/2, so we were contracting by 1/2 the sides. We can deduce, we identify the scaling factor, and E comes from escala in Portuguese, it's not really. So this should be S in English, the scaling factor. So when there's self-similarity, we identify the scaling factor and D will be log of n over log of E. Essentially is that. So let's see an example. So here we have 4 examples. So the objects that I'm presenting here, the 4 objects, are the after iterating a process, so we have a process in the 4 cases, and after iterating the process infinitely many times, what do we have in the end? The limit of this process, okay? Like in the Sierpiński triangle, that burst of points that resemble something like what we had before. So here the process is, you divide think that this is an interval, again, segment. Divide it into 2 parts and throw away the right-hand side, okay? Well, if you iterate this infinitely many times, what you have in the end, at one point here, is the one that remains. Any other point is going to be thrown at some stage. Here, you divide it into 2 parts and you don't throw anything away. So in the end, you obtain the same. So here, you obtain something, dimension 0. Here, you obtain something, dimension, the same dimension 1. Okay. Here, you do, well, this is very famous picture in mathematics, very important in mathematics, is the middle third Cantor set, as a name due to Cantor, one mathematician. So here, what is the process? So you divide it into 3 parts and throw away the middle one, okay? And then do it again. And here divide it into how many? 5 parts and throw away those 2. So in the first one, we have what remains, this scaling factor is 2. So log of 1, so remember the formula was log of n over log of E. Log of 1 is 0, so it's 0, the dimension. Well, it matches. For the second one, well, is log of n over log of E, well, is 1 because it's the same quantity, and it matches our notion of dimension. For this is more interesting. This is the first fractal dimension that appears, because it's log of 2 over log of 3, and it's around 0.63. Okay? For this one. For this one is bigger, it's 0.68. So we have here procedures, and we obtain objects with dimension, with this generalized idea of obtaining dimension, which is not 0, 1, 2, 3, as in the classical geometry. Well, we can do this kind of constructions now in dimension 2. Well, again, we are dividing many parts. So for 1, for instance, we obtain 0 because again, we divide in many squares. We take just 1 and divide it around. This 1 in the end, the only point that remains is this 1. Here, what will be the dimension? Well, we are dividing, and here in the center, this length here is equal to this length is equal to this length. And we go then, in the end, we obtain dimension equal to 0.63. But what remains is essentially this kind of set, but here in the diagonal. Okay, will be contained, actually the limiting set will be contained in the diagonal of this one. So here we obtain, it's easy to see, we obtain a line, so dimension will be 1. Here we obtain something in between 0 and 1 and 2, close to 2. Here we obtain dimension 2. Okay? So this is a way of introducing dimension that can be generalized to more irregular objects, not just the line spaces, the lines, planes of spaces, things like that. Well, more example. Here we have the one that appeared, curve that is before. So n is 4 because we take 4 parts. The scaling factor is 1/3 for each, so dimension is 1.3. Here is the space filling curve. And if you see, well, n is 9 because we take 9 parts. The scaling factor is 3. And so log of n squared, which is 3, n, which is 3 squared over log of 3, the dimension is 2. And it matches because it's a space filling curve, so it gives a plane region. For this one, the Sierpiński triangle, the dimension is 1.6, around that. It's not exactly that, but always approximations. Here, for instance, a kind of Sierpiński cube, the dimension is around 2.7. Well, we can do iterating processes in this way. So we go there and replace each by something of that type. And we obtain, in 18 iterations, we obtain some which seems filled. And dimension is actually 2. It actually fills some two-dimensional region. Well, back to coast. So there are some good computations of the coasts. Great Britain comparing this. 5 is the most irregular, 1 point around 1 point. This is not exact, so this is approximation, application of the field. So Germany is less irregular, so a bit more regular. Portugal is somewhat the coast, and Australia. This is somewhat more smooth. South Africa. Well, now the picture of the first slide, Mandelbrot and Julia. Well, it has to do with complex numbers. For those who know, this is just a trivial slide, but well, complex numbers, for those who don't know, is you can identify the plane, the two-dimensional plane with the complex numbers, think that they are vectors, and we define an addition. So the two components are x and y, so we think of two components, and we add them exactly as we add vectors in usual R2. The new thing here is we introduce a multiplication of vectors. And the multiplication is, you act as if these were real numbers, and you use the distributive property and do everything, and using this rule, that I squared is -1. And so in the end, the multiplication of this times this is precisely this. This is very important in mathematics and physics and fields. This is the complex numbers. So this generalized, so we can think of R as a subset of C, which is the plane. We can think of this line as a subset. And these operations, they generalize the operations that addition and multiplication that we have now. So we can define iterative processes. So we fix a parameter, and imagine that you square the complex number and you add the parameter. So this is the transformation. So you start with certain Z0, and then you have Z1, which is Z0 squared plus C, and so on, and you continue. So this sequence, so you always use the same rule, square and add C. So this sequence is called the orbit of Z0. Well, it's not difficult to see that, so for C equal to 0, we have this 0 remains 0. I goes to -1 because I squared is -1, -1, I is a real number, so it goes to 1 and so on. So 2 goes to the square, which is 4, 4 goes to 16, and it goes to infinity, it goes away. If number is inside the unit circle, 1/2, for instance, it goes to 1/4, because these are real numbers, the rule is the same, so it's generalized. So orbits of points outside the unit circle, they are attracted or go to infinity, they go away. Orbits inside the unit circle, they remain inside it. So the unit circle separates two distinct behaviors, and it's called the Julia set for this parameter, C equal to 0. Okay? For other parameters, the Julia set can be much more complicated. And here I show you other Julia sets. So the previous one would be a circle, black inside and colored outside. So we have for this parameter, so here C 0.6, somewhat regular, but can be very regular. And that they are distinct, the ones above and on. So these are connected, so they're not separated parts. These are disconnected, so they have many components. And here is where Mandelbrot appears. He proved that the Julia set is connected if and only if the orbit of 0 does not escape to infinity. For instance, for 0, the orbit of 0 does not escape to infinity. It's fixed, the point. It remains 0, 0, 0, 0. So the Julia set is connected, which is clear. What is the Julia set for C equal to 0? The unit circle. There's no separate pieces. Okay? And here, let me see if I can show you the movie. So this is the Mandelbrot set. It's the set of parameters, so this is the complex plane. The set of parameters for which the orbit does not escape to infinity. So this is the black part here. Okay? I think it's not going to work.
Okay.
But I think we don't have much time, so the movie was, we would zoom here and you see, but you can see even here that here, for instance, you have a copy or something like the whole set. So you was zooming at several scales and we could see. So this is a very rich fractal set. Actually, it has several interesting. So here I'm zooming, what I'm zooming is not the set there, it's the Julia set. So they are all connected because it's inside. So the Mandelbrot set is the black part. Okay? Facts, it's connected, so there are no separate pieces. The boundary is, the border is 2D. It's not, it seems like a line, no. It's very complicated. It's like that Koch curve. Very two-dimensional. Conjecture, a very important problem in mathematics, in this field, is locally connected. So if you go locally, is it connected? There is a, for every point, a neighborhood. This is still an open problem. Well, let's go now to the three applications. Applications of the ideas, so approaches to art using these ideas of fractals. The first one is painting, actually related to paintings of Jackson Pollock. Well, it goes to a published paper by, I would say, Taylor and several collaborators. I say Taylor because he has more works on this than the other ones, but in this case, there's a paper by Taylor and these two collaborators. They analyzed, actually there's for that painting that Pollock was doing there, there's a little movie, and they analyzed as if the moments he was painting were the iterating processes. They used that as the first reference. They used computers and the layers of that Pollock, with his stripping method that he used, very characterizes his paintings, and used the layers in different colors, used computers, and using those layers as the iterating process. Okay, so the idea is always the same, and they analyze this painting. So this is just an abstract. It has nothing to do with the painting. It's just an abstract way of defining how they work on this. And they analyze the movie in several moments. And in the beginning, there was no fractal. So the idea of fractal is that it does not depend on the scale, like the line or the square that we analyzed. There was always 1 over L squared, or 1 over L to the 1. In the beginning, there's no fractal structure, but then it does not depend on the scale. There's 1 over L to some power, fixed power. And so this is after 47 seconds. This is the moment, analyze the fractal. So there's a threshold after which it's essentially a two-dimensional object. If you use large scale for something like this, two-dimensional. So in all cases, they identify the moment after which. And so for the last case here, the moment is 32. So there's a certain scale. I don't know what is it's in millimeters. So after this, there's no distinction between solid square. But up to this moment, it does not depend on the scale. There was 1 over L to a certain power, and the power is this. Of course, this is application of mathematics, so it's just using the ideas up to a certain limit where it makes sense then. So and there's always this resolution threshold. And they analyzed many other paintings by Pollock. And you see, as time goes by, the dimension is increasing. I read something, actually I started to like the paintings of Pollock because of this scientific work. I must say that I never paid much attention to Pollock before, and after this is one of my favorite painters. And you see the dimension increasing. I read something that, well, in abstract art, we go identify, look at some abstract painting, we identify, oh, well, in the clouds with my kids, I do, oh, rabbit, well, somehow. One of the goals of Pollock was that people looked at the paintings and did not identify anything. Was one of the goals. Okay, so you see over time that dimension is increasing. And to the best of my knowledge, this has already been used as a criterion for discarding certain, you know, that famous paintings, famous painters have many, sometimes paintings attributed to those painters which are not, so they try to verify if it's fake or not. And I read somewhere that this has been used as one of the criterions to discard some painting because of the year, the dimension didn't match that period. Okay. So paintings, you see these ideas of fractals being in art appearing and having some roles. And another thing, so I'm not claiming that Pollock was having in mind fractals to paint. The theory was not yet developed. Even though some of the ingredients, going back to Hilbert, for instance, or Cantor, were already there, but not as a theory. Actually, just there was some published, some journalist published something about the painting of Pollock saying chaos, damn it. And chaos at that time was a bad word. Nowadays, when I can, I put chaos in the titles of my talks because it's somewhat attracting. But at that time was something bad. Jackson Pollock wrote for that same magazine some text saying non-chaos, damn it. Just to see that the word chaos, which was not very well seen, nowadays is very well seen, the chaos theory and so on. Another example, music, here by Bach. So this is this Bourrée, number 3, and it has fractal structure. Actually, the composition is divided into movements A and B. A is repeated, these 2 dots, and the A movements are divided into red, the red mark. So this is essentially the same, not in terms of the note, is note, tone, not in terms of the tones, but of the rhythm. So this is the same of this, and then there's the same. So, and here, each of the A's, which are in red, you see again, A, B, A, B. Okay, so you see this structure. So, going back, relating to Cantor set, we exclude the middle third, and we have this notation, we can notate it in that way. In the Bach set, we could have it described not as ABA, and then BB, because this is the part that is removed. Okay, so the B's are the removed. He is not removed, but this is different, okay, structure. So he is AAB. So we have this kind of fractal structure in this piece. And then finally, literature. So this is the Sale of Ulysses by Wallace Stevens. And the root known, not necessarily the word known, but the root known, knowledge here, known, appears in a certain fractal structure. Here we are like, oops, that it should be there. Okay, no problem. So, so you can actually, in some sense, it organized, because here we have the first 4 and here we have the second 4. So they appear. So they divided in this. I don't know who is they. Well, I should have. Well, in the bibliography in the end will appear. So we can see kind of ideas of fractal construction of fractal sets. So no, and then second group no, and some space no. Okay. So you see these clusters where the root appears. Of course, it's not infinite iterations. It stops there. But you can see in a first iterations. And here's different. So this is from Robin Chapman, writer, I think professor at some American university. And here, differently from the previous art pieces that we analyzed, like the paintings, the Bach and the Sale of Ulysses by Wallace, here was written specifically having in mind the Mandelbrot set, and she called it Escaping the Mandelbrot set. Well, so we have these parts of the poem, and it begins with she says, as if an iterating process we have. And then it appears coffee, certain scale, today's weather, bigger scale, summer, even bigger scale, and wedding, which, well, in principle should be even bigger scale than summer, but sometimes it's smaller. But let's think of, statistically, I think it's bigger than summer. Okay? And then why escaping? Because then she comes back to the scale of coffee with the cappuccino. Okay? So it breaks. So that's why she says escaping the Mandelbrot set. Okay, so this is, I hope I can introduce for those who don't know about fractals, some ideas of fractal sets. For those who know, some new ingredients around fractal sets. And I finish with the sentence by Poincaré that scientists doesn't study nature because it's useful. It has to do with the usefulness that we are always, in fundamental science, this is sometimes dramatic. Is usefulness. Usefulness sometimes takes a long time to be useful, but in general, the mathematics, the good mathematics we produce is always useful. In the future, there will be a moment when, and you say that the study because it takes pleasure and takes pleasure in studying nature because it's beautiful. Right? It's one of our main motivations is the beauty of things. And that's why we appreciate so much art. It's ironic that usefulness and what is most paid, well, one of the most things, paintings, for instance. Those painters did something completely useless. And now they pay those amounts of money, so think of that. Okay, thank you very much. So here is the bibliography.